Welcome to the video on the introduction to differential equations. What's a differential? Well, we've been doing things like, if I said that y is equal to, I don't know, 3x. If we took the derivative of both sides of this equation, we said, one of the notations we used is we said dy over dx is equal to 3. We took the derivative of both sides of that. But this you could almost use as differential notation. dy is a differential, and dx is a differential. And what does a differential mean? A differential just means an infinitely small change in y in this case. So that's the differential in y, or an infinitely small change in x. So a differential, it's like a difference, right? When we learned slope, we said, slope is change in y over change in x, or you could say the difference in y over difference in x. But once we started taking the slope of curves, we had to make this difference and this difference approach 0. And that's what a differential essentially is. A differential is a really infinitely small difference. So what is a differential equation? Well, it's an equation that involves differentials. So for example, this is a differential equation. This will be the first example that we solve. dy over dx is equal to x squared plus 1. And so how do we solve this differential equation? Well, there's a couple of ways you could say it. You could say, oh, well, this is the same thing as f prime of x if, y was a function of x, and you just take the antiderivative of both sides. But let's solve this properly as a differential equation. So you can actually manipulate these differentials the same way that you would manipulate numbers for the most part. And so what can we do here? Well, let's multiply both sides of this equation by dx. So you get, for a very small change in y, dy, you get x squared plus 1 times a very small change in dx. Or another way to say it is, for a very small change in x, if you want to figure out how much does y change, you multiply times x squared plus 1 wherever you are on the curve. So what does that do for us? Well, let's take the antiderivative of both sides, or let's take the integral of both sides. And if you watched all of the videos on integration and the definite integral and area under curve, you realize that an integral is essentially a sum. It's kind of an infinite sum of a bunch of these infinitely small dy's. So if you take the sum of all of the changes in dy's, you're left with a y on this side of this equation. And you might want to rewatch all the videos that we did on integration. And then what is this? This is essentially just, this is the indefinite integral of x squared plus 1. So it's the antiderivative of that. And what's the antiderivative of x squared plus 1? Well, it's x to the third over 3. And we're just taking the derivative backwards. And once again, watch the videos on the antiderivative. There's, I think, 8 or 9 of them. Plus x, and then plus c. And where does the c come from? Well, we know that when we take the derivative of a constant, it goes to 0. So when you take the antiderivative, we're like, well, there could have been a constant there. And that's where that plus c comes from. So this is the general solution. This is the general solution to this differential equation. And that's something interesting. So with traditional equations, the solution tended to be a number. Right? If I just told you, y is, if I told you, y is equal to 2y minus 1, then you'd get minus y is equal to minus 1, you'd get y is equal to 1. So this is a traditional equation, and your solution was just a value. You solved for the variable. Differential equations are something different. The solution is actually a function. You're saying, what function satisfies this differential equation? So that's something to keep in mind. And right now we're doing very basic differential equations, but that's something to keep in mind the whole time you learn differential equations. I think I'll eventually do a playlist on essentially an introductory course on differential equations that you would take at college, and that applies even when you start doing partial differential equations, etc., etc. It's the solution to a differential equation is not a number; it is a function. So anyway, this was the general solution to this differential equation. And then if you want the particular solution, people normally give you initial conditions, or they give you points on the function, and then you can substitute back. So in this problem, they said that dy dx is equal to x squared plus 1. And then they said that, let me switch colors. They said that y is equal to 1 at x is equal to 1, or y is equal to 1 when x is equal to 1. So we can use this information now to solve for c. How do you do that? Well, it says y is equal to 1. So 1 is equal to, when x is equal to 1, is equal to 1/3, right? 1 over 3, 1 to the third power over 3, plus 1 plus c. And let's see what I can do. Subtract 1 from both sides. This becomes 0. Subtract 1/3 from both sides, and you get c is equal to minus 1/3. So using these conditions, a point where this function crosses through, we can now give you the particular solution to this differential equation. And that is y is equal to x to the third over 3 plus x minus 1/3. And we just solved for this c. And if you don't believe me, take this expression and substitute it here, and you will see that it equals, if you were to take the derivative of y with respect to x, you would see that it equals x squared plus 1. Let's do another one. So it tells us, and this is a little bit more interesting, it tells us, it says dy dx is equal to x over y. And it says, well, it has the same condition. So it says y equals 1 at x equals 1. Or when x equals 1, y equals 1. So let's find the function that satisfies this equation. This one's interesting because we have a x and a y on the right-hand side of this equation. So this kind of looks like something we got after we did some type of implicit differentiation. But let's see where we go. So let's do the same thing. Let's multiply both sides of this equation by dx. And so you get dy is equal to x over y dx. And let's get this y over onto the dy side, because it'll be easy to take the antiderivative then. So we get y dy is equal to x dx. Now we can take the integral of both sides of this equation. Take the antiderivative on this side with respect to y, on this side with respect to x. I don't know why I did it in brown. So what's the antiderivative here? Well, it is y squared over 2. And I could say plus c, some constant. Let me do that. There could be a constant here. I'll call it, I don't know, I'll call it c1. We don't know what that constant is. And that equals x squared over 2 plus c2, right? Some other constant. Maybe it's the same number. I don't know. But we don't know what either of these are. I could rewrite it as, let's see, what could I do? I could, well, let me take the x onto that side. So I could have y squared over 2 minus x squared over 2 is equal to, and let me subtract this from that side so I get the constants all on the right-hand side of the equation. c2 minus c1, right? Just took the c1, put it on the right-hand side, took the x squared over 2, put it on the left-hand side. That's why it's negative. And we didn't know, we said this could be any constant and this could be any constant. So the difference between two arbitrary constants could just be a third arbitrary constant. So I'll just rewrite that as c. And so the general solution to this differential equation is y squared over 2 minus x squared over 2 is equal to c. And actually, let's do something else just to clean it up a little bit, because once again, this could be any constant. So let's multiply both sides of this equation by 2, and you get y squared minus x squared is equal to 2c. Well, now this is still any constant number, so we could still write this as a c. So we have y squared minus x squared is equal to c. Now let's use our initial conditions to see what c is. So when y is 1, so 1 squared minus when x is 1, 1 squared is equal to c. Well, this is 1 minus 1, so it's 0, right? c is equal to 0. So what is the particular solution to this general equation, to this differential equation? I'll do it in green. It is y squared minus x squared is equal to 0. Or we could add x squared to both sides of that, and we could also write it as y squared is equal to x squared. Now you might be tempted to take the square root of both sides of this and say that y is equal to x. And the reason why this would not be accurate is because here x could be minus 2 and y could be plus 2, or vice versa, right? So this would satisfy this equation, but it would not satisfy this equation. So be careful when you take that square root. You have to worry about the plus or minus. Let's do one more. Let's do one more. So this one says the derivative of y with respect to x is equal to, this is the square, okay, so this is even a little bit more interesting. This is equal to the square root of x over y, the square root of x over y, and it says that y is equal to 4 when x is equal to 1. Right? Yep, I think I'm reading that right. Well, we could do this one very similarly. So let's just do the same step. So multiply both sides of the equation times dx. So you get dy is equal to, and I'm actually, just to skip a step, I'm going to rewrite square root of x over y as the square root of x over the square root of y. And I multiplied both sides of that times dx. And now let's multiply both sides of this equation by the square root of y. And I'm just going to rewrite it as y to the 1/2 power. Right? That's the same thing as square root of y. dy is equal to x to the 1/2 power dx. I just multiplied that there and rewrote it as y to the 1/2. And so what is the antiderivative of y to the 1/2 power? Well, it's just this plus 1, so it's y to the 3/2 power, y to the 3/2 power, and then times the inverse of this, so times 2/3. Or you could have said divided by this, either way. And if you're not sure about this, because sometimes it is confusing with the fractions and whatever else, take the derivative. 3/2 times 2/3 is 1, and then you subtract this 1 from the exponent, and you get y to the 1/2. So that works. And of course, we kind of go through the same drill. Plus c1 is equal to, it's going to be the same thing on this side, 2/3 x to the 3/2 plus c2. And what can we do? Well, let's take the x to the left-hand side of this equation. So we get 2/3 y to the 3/2 minus 2/3 x to the 3/2 is equal to c2 minus c1, which we can just rewrite as, c. And let's multiply both sides of this equation by 3/2. So these two will become 1. So you get y to the 3/2 minus x to the 3/2 is equal to, well, what's 3/2 times some constant c? Well, we didn't even know what it was. We haven't solved for it, so we can still write c. I hope that doesn't confuse you. 3/2 c, we didn't know what it was, so we could call this c3, and now this is c4. It's a different constant, but we still have to solve for it. And now let's use our initial conditions. So the initial conditions tell us that 4, and they don't have to be initial conditions. You can just kind of say conditions or points where we know that the function, the particular solution to this differential equation are satisfied. So 4 to the 3/2 minus 1 to the 3/2 is equal to c. What's 4 to the 3/2? So 4 to the 1/2 is 2, and then that to the 3 power, that's 8. And then 1 to any power, but especially in this case, 1 to the square root of 1 is 1, and then to the 3rd power is 1. So 8 minus 1 is equal to c. And so c is equal to 7. And so the particular solution of this differential equation I will do in a different color, and it is y to the 3/2 minus x to the 3/2 is equal to 7.